Hey, and welcome to Physics 2212 Lab 4 by me. All right, so the purpose of this lab was to measure the distance dependence relationship of a magnetic field of a small bar magnet. And then we made a computational model and we compared the two. And we used our phone, we used a magnetometer app we downloaded on our phones for this purpose. So the fundamental principles that this lab runs off of are one, the Biot-Savart law, which is just the magnetic field of a point charge, which is kind of how we derive all of our other magnetic field relationships. And then we have the formula for an off-axis magnetic field, which is going to be important for the second part of the more computational part of the lab, and the distance dependence relationship of a magnetic field, which we use to find a bunch of things, to be fair. It's a lot of the lab. Okay, so our system is the bar magnet and the phone magnetometer. The surroundings, which we're going to have to deal with, which we're going to have to account for, is Earth's magnetic field. And our initial conditions is that mu naught divided by 4 pi is 1 times 10 to the negative 7th, which is kind of just a fact. So basically, to deal with the Earth's magnetic field, we're going to align our phone with the north magnetic field in order that our x component is basically unaffected by that. And then we're going to take our measurements with that so that we're only measuring the magnetic field of the bar magnet, not of the bar magnet and the Earth. So here is our data. Here's our on-axis data. As you can see, we have the distance when the electric field is 20, what is that? Like microteslas, I think. 20 microteslas, 70, 120, and so on and so forth. And as you can see, the distance decreases as the strength increase, as the force as the magnitude of the magnetic field increases. And as you can see, we got a little graph here. As you can see, that relationship there, y equals negative 8.926x minus 13.789. That we can plug into an equation, which we have on this page. And as you can see there, my math on the bottom, we can say that distance cubed times 2.07 times 10 to the negative 4th, which is e, which is the e raised to the k value found over here, is divided by 2 times mu naught over 4 pi, gives us mu, which I found to be 9.683. And here's our off-axis data, just as well. And here's our here's the code for the computational portion of this lab. Yep. So we have the dipole B. This is where we put it. This is where we put in what we found the magnitude of mu to be. Here's where we define the magnetic field of the B field from a dipole. B scale is just kind of scales the lines so we can see them. Here's where we put our observation points. Here's where we display our observation points. Yada, yada, yada. You all know how this goes. And here it is. So we've got our on-axis. We've got our 2 orange things on-axis. We've got our 4, I think cyan. Yeah, that's what color that is. Cyan arrows on our off-axis. Now you can't see one of them because it's behind. It's in the negative z direction, or it's on the negative z-axis. And you can't really see that because there's a thing in the positive z-axis in front of it. But it's there. You're going to have to kind of believe me. And then the pinkish one, I think that's magenta. Magenta one is our 45 degree off-axis one, proving that it works. All right, for potential errors, potential sources of errors could be the magnetic field of Earth if we didn't align it properly, or we lost our alignment during the lab, or we messed up on where the exact location of the magnetometer was in the phone, and our distances are off. Some of our observations, we observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x directions, and as you move the magnetometer closer to the magnet, the measured x component of the magnetic field increases. The other two that they provide are, for that part, we did not observe. What if we hadn't oriented our experiment to compensate for magnetic north? Basically, our measurements would have been skewed because they would have been measuring some component of the Earth's magnetic field and the bar magnet, but we didn't want the Earth magnetic field. And if we were to stick the 2 magnets together end to end, we would get twice the magnetic field in the same direction. That kind of just makes sense. All right, thank you for watching. Goodbye.